What's up, everybody? Welcome to Geology. So we're going to get into some topo maps today, topographic maps. This is the lab. I know 11 pages looks like a lot, but I kind of like work the notes into it as well, the ideas. So you're not going to be doing 11 pages worth of work necessarily. Space it out so we can do some examples and see what's going on. When we get down to questions that you have to do, if you're going to do the lab down here, I'll show you what to do with that because you guys can't mark up these PDFs. We'll talk about how to do that. So stay tuned in the video. We'll figure that out. First off, let's just say, what the heck are these maps? So if you were to take a landscape that kind of looks like this, right? This, if you could picture this, how do you take a three-dimensional surface of the planet and represent it on a two-dimensional piece of paper with standard rules so that everybody knows the score and everybody knows how to interpret these things once you pass that off? That's what they're doing with these diagrams, both this one and this one. So what I'm going to say in a few minutes is to pause this and to really take a few minutes and just compare, look for features here, and see what they look like. If you don't play with these and discover them a little bit, it's going to get a little tricky fairly soon. So notice things like, hey, when there's a steep cliff like right here, what does that do to the spacing between the lines? Where it's flatter, what does it look like? A couple of things like that. Do that for both of these. This landscape goes with this map. This landscape goes with this map. Okay? Simultaneously, I printed from two different sources or added from two different sources the rules for contour lines and for topographic maps. Okay? So those first 4 pages of the lab, I'm going to recommend checking it out, going to the rules, checking it out, going to the rules. Look for examples of these rules up in there. I'm not going to necessarily read through all of these in the video because I think it would just take too long, put you to sleep. That'll be your job. So pause the video here, take some time and do that. We'll see you back in a minute. Okay, now that you're back, welcome back. And let's talk about what you're going to do now that you've gotten through all that stuff. I'd like to just mention 2 things that I think are a little like the less intuitive things out of all those rules. One is depressions. When you see these little, we call them hasher marks, little teeth pointing in, that means that there's a depression in the ground. So like this, a pit. You see these with places where there's been mines, there's naturally pits sometimes, craters, things like that, right? The unintuitive thing is that if you're getting down the spacing and how it works, you might say, okay, we're going from 200 to 220 to 240. The big mistake is that people say, oh, this is a downhill, so it must go from 240 back down to 220. But it doesn't. It repeats the same value again. Because as you're walking uphill, you might go to 240 and then up above that a little bit. But then as you enter the hasher marks and start going down below, to go below you have to cross 240 again. So those two are going to have the same value. Now, if we keep going down like that, you'll go down past the 220 or whatever the values are specific to the map you're looking at. And then up to the 220 to the 240 again, which would mean that you've crested the hill again. You go to the top and you're going to come back to 240 once again. All right. That's a little tricky, but use this and this to try to visualize that. Another one is what happens in rivers. And I know this is up here, but wherever there's a river, what happens to the contour line itself? I'd rather look back up at, this rule explains it pretty well right here, and it's nice and visual. Let's go explain it using this guy and maybe zoom in a little bit. See this 100 line? Where the river flows, and in this case, it's very easy to tell where the river flows because water flows downhill. So it's going from a higher elevation down to a lower elevation, right? There's instances, though, where there may be questions where you don't have the numbers. So you have to be able to say, oh, looking at this contour line and seeing that it goes like that, that is going to let me know where the river is. Now, the rule itself, again, may be a little counterintuitive. We say that the contour line makes a V. Now, the thing with the V is that people in their head want to picture this as an arrow because it looks like an arrow. It's not an arrow. It doesn't show you where the water flows with that V. It actually shows you where uphill is. Now, the reason is that as this river flows and erodes sediments, maybe this contour line would have been straight across at the time. But as it picks up sediment and drags it downhill, as rivers do, it makes the elevation creep its way upstream. So these arrows, they're not arrows, they're V's, point upstream, and water flows downstream. So see all those little V's? They point that way. But if I had to say where the river was flowing, the river's flowing that way. Opposite the direction of the V's in the contour lines. Deal? All right. Don't let that be it. Again, I hope you press pause and checked all those out and then went back to the map to look for examples of that. What else are we going to have to do with these maps? Well, latitude and longitude is going to be printed on them. The hardest part of this lab is going to be dealing with local maps. I ended up just using the Fulton one. The original lab had ones from Fulton and Oswego. I'm going to put them both into the folder, but you're going to mainly use the Fulton one here and look for different features. Talk about some of the stuff at the bottom. But latitude and longitude is going to be part of it. So let's just, in case we don't have it down. Sorry. There we go. Do a really quick review on what latitude and longitude are. So latitude runs this way, like the equator, north-south, and it actually tells you, in the northern hemisphere particularly, the altitude you got to look up at to see Polaris, to see the North Star. I can point at Polaris right here in this room, even though there's a ceiling and it's daytime. We can't see the star. I know right where it is because I know where north is and I know my latitude. So by going up at that latitude, there's Polaris. So latitude is a measure of the altitude of Polaris. Longitudes were much trickier to figure out. It took until we had really accurate means of timekeeping to figure out longitudes because it has to do with the Earth spinning underneath the sun, which is, there's ways you can measure it, but if you don't know exactly what time it is, it took a while to figure this out. Now, we're not going to go too hard into the nitty-gritty on this, but you'll have to figure out latitudes and longitudes of some points on the map. And it looks like I went in the wrong order here. Let's pop to that one. For example, and the way that if life were simple, we would just do this in decimals because I think everybody's comfortable with decimals, but life's not always simple. We use degrees, minutes, and seconds. So there are 90 degrees of latitude from the equator to the pole, and then each degree is broken into 60 minutes, and each minute is broken into 60 seconds. In theory, it's no different than using a decimal, right? I mean, a decimal is easy to picture. 40.44, we can all imagine what that is. Like if you have $40.44, that's what it is, right? It's 40 and then 0.44 of the next thing. This is a little bit trickier to picture, but it's really the same concept. Here's the degrees, and then break it down into smaller units after that. 26 minutes and 46 seconds would be, for example, a corner of a map. Okay, so there will be questions when you get to the Fulton map. Let's go back to it. That deal with that. Looks like they did it in minutes here on the map. I'm sorry, in decimal on the map I gave you. So, hey, that makes life easier. Congrats, because it's a lot harder to do in minutes and seconds. So that's going to be easy. Just check those numbers. You'll be in good shape. Okay. Let's talk about scale quick. Whenever there's this kind of ratio, what it means is that one thing equals that many of the things on the map, right? Obviously, with a map, we take a larger area and we shrink it down. So you want to do it in inches. 1 inch is 25,000 inches on that map. You want to invent a unit, fingers. One of your fingers would be 25,000 of those fingers on that map. So those will generally be printed on the maps. Check it out right down here. So you'll have to do a little bit of work with this. One place where I see people occasionally get tripped up is that these look a little funny. Note where the 0 is in these. So like this mile right here, right? 0 miles, 0 to there, that's 1 mile. And then 0 to 1 there, that's another mile. So the whole entire line there is 2. They just break it down by tenths on this side. It looks a little funny, but once you get used to it, that's no big deal. Same with meters and kilometers. They got 0 here, 1, 2 that way, and then 1 that way. No big deal as long as you know. Don't just assume that, hey, I'm going to put my thing here and that is 1 mile. It's not. It's 2. Be careful with that. You'll be in okay shape there. What else we got? Now, there's this cool thing. When we get into the layers of the Earth inside, we're going to talk about what's going on with magnetism. For now, note that there's a difference between what like the North Pole is, what our like rotational axis is, what we call the North Pole, and where the magnetic field produces a North Pole, they're off by a bit. They're not right on the same spot. So this little image, which is actually from the REI website, it was just the kind of simplest one I found, just shows us that hey, if you have a magnetic compass, it points to the magnetic North Pole, not to the geographic North Pole. So you got to know that difference and account for that if you want to do accurate plotting with a compass. So compasses have a way to offset this. This is called declination. It says it right there. How far off are those two? And depending on where you go on the planet, they're different. So people that are like way into orienteering or making accurate maps or doing accurate geologic maps know that, and they can offset that screw and correct for the declination at the spots. So I asked a quick question about that on the lab. It's down to the bottom of the map. These little arrow guys right down here. Check that out. See how you do there. Okay. All right, so I think it's time to get to work. That went faster than I thought. Hope you're still with me. So here's what I did. This is going to be a PDF. This is actually because somebody did it this way on the first lab, and I think it's the best way to go. I'm going to have a separate answer sheets in Google Docs, and you can just plug the answers on this onto that, right? So this will just be downloadable, but what I'll do on that is I haven't set it up yet. I'll do it in a moment. It'll say like, and that's why I put page numbers on here. So page 9, 1A, and I won't reprint these questions. There will just be a spot for you to answer. So that won't be that long of a document. You work your way through these questions. There will be places to put them on the answer sheet. You understand what I'm saying? So this you'll have, but you don't have to, you're not going to hand that in. The answer sheet will be the editable one in Google Docs. You can work through those questions. So these are fairly simple, like ones out of a workbook. A couple places where they're funny. It says to like label them on here. Now you can't do that, right? Because if we were in class, we had paper and pencil, we would. But in your head, label them. These questions then are answerable. And if you're like, oh, I see some vocab here, I'm not recognizing what the answer to that is, everything should be like up here in these rules. So if you didn't do that, pause and go back and read those. Do that before you try this stuff. And the type of feature, I think, is just a hill. I thought that was kind of a silly question, but these ones are solid, so try those ones out. And again, there will be slots on the answer sheet. And again, this is really just a hill. Don't worry about that. But those questions, again, will be okay. All right. Then we're going to play with local topographic maps. So there will be an image file, JPG, of this right here. So open that up in something you can zoom in and out on. You're going to have to look for some fairly subtle places on here as you work your way through it. And it's going to have you working the shapes of some hills, the differences in elevations, and even the steepness of some hills, and some of the stuff with rivers. All right. It's going to take a few minutes. It's not going to be a quick assignment, but if you open this up, open up that map, have this open. Again, the answer sheet will have spots for all these answers. Work your way through it, take your time. You should be able to figure it out. Okay. Even getting into the gradient. Now, I think hopefully it's explained well enough here that you can figure it out. Gradient is really a measure of how steep a hill is. And you're going to do it for, in fact, let me hit pause and open something up. I'll show you an example of it so that it's obvious. All right, so let's do it. How do you do one of these gradients? It's a mathematical measure of how steep a hill is. So I'm going to a ski slope in upstate New York. If anybody's a skier, and don't worry if you're not. This is Labrador Mountain. So if we were up at the top of Labrador Mountain, top of the chairlift, which, I don't know, somewhere right around here, is at an elevation of 1,826 feet. And then we go down to the bottom, and it's at an elevation of 1,184. So we go 18, look at those numbers, 26 minus 1,184. So if you go skiing there, how much did you, we need my calculator anyway. How much did you go up and down? Up and down by 642 feet. All right, that's the change in elevation. That's how much downhill you went. Now, that's not all of this, right? What's cool about gradient is that it's a measure of steepness. If you were to do those 642 feet over a distance of a tenth of a mile, you'd have to be going straight down. If you were to do those 642 feet over a distance of 30 miles, you would barely even notice that it's a slope, right? So this is, in fact, if you've heard this word slope, it's basically what you're doing. If you've calculated a slope in math class, it's how steep is that, right? So we've just figured out that from the bottom of the chair to the top of the chair, over there on that trail is called Badger, is 642 feet. And again, kind of the magic number for how steep that hill is going to be is how far do you travel over the course of dropping those 642 feet. Google Earth can help us out with that because there's a measurement tool. I'm going to do it in miles. Say from there to there, they're giving us 0.65 miles, right? So they want 0.65 miles. So a gradient, like it says in your lab, which I'll come back to, is that divided by that, and that's it. So 642 feet over 0.65 miles. Our answer is 987.7. Labels, just copy what you already did, feet per mile. So that number means that over the course of that trail, and granted, that trail has some sections where it's steeper and some sections where it's flatter, like that line is a little bit wavy, but over the course of that trail, for every mile, you're changing elevation 987 feet. That's a green circle trail. That's an easier one. Go to a black diamond, we'd expect that number to go up. You're going to be going over a steeper hill, right? So like more of an elevation change over the same distance or the same elevation change over a shorter distance, whatever it may be, a steeper hill. All right. That's what you're going to do in the lab. You're going to do it for a couple places that you'll already be playing with in the map. Give me the change in elevation between the 2 points, divided by the change in distance between the 2 points. Hit them in a calculator and you got your answer. Okay. That's a gradient. The other thing, I just really couldn't come up with a good way to do it online. But what we really should do, and I think I'll have some questions when we do, if I do, which I'm looking at doing a quiz for this section, is what's called a profile view. So a profile view is looking at something from the side. If I were looking at this hill from the side and I sliced from A to A prime right here, and I looked at it just that, like if you could cut that into the earth and scrape away the rest and look at it from the side, what would it look like? You can do these very exactly by drawing with pencil and paper and saying every place where it hits a line, we put a point on this graph, and then you can accurately do what that would look like. Now, there is a pretty good vertical exaggeration with these. They blow them up so that we can see the difference. But nonetheless, that gives us what a profile view would look like. I couldn't come up with a good way to do them online. So I'm not going to have you actually make any, but I may have you try to recognize what some would look like based on that idea. All right. What do you think? Give it a try, and let's see how it goes. Shoot me an email if you have any questions. Thanks for tuning in. We'll catch you soon.